You know what's funny about space? We spend all this time worrying about the little things. Asteroids the size of buses. Comets barely wider than a city block. Meanwhile, something the size of a small country has been gliding toward us from the darkness, and we only just noticed it hiding in old survey data. While NASA tracks 3I Atlas like it's the main event, Bernardinelli Bernstein, a 137-kilometer ice mountain 10,000 times more massive, is already halfway here. It woke up at 16 astronomical units, billions of miles before it should have. Super-volatile jets erupting where nothing should be moving at all. So here's the question nobody's asking out loud. What kicked it loose? And is it alone? Stay with me, because the Oort Cloud isn't sleeping anymore, and something massive is hurtling towards us in a trajectory that has put even the calmest scientist on edge. You'll want to stay close as Bernardinelli Bernstein continues plunging into our solar system and the data keeps rolling in. Subscribe and follow along, because every new observation brings us closer to understanding what we're actually looking at here. Now let's dim the lights and dive into this cosmic mystery together. You probably heard about 3I Atlas, the interstellar visitor that got everyone's attention, the one that made headlines, the one that had NASA scrambling to point every telescope we've got at a tiny speck racing through our cosmic backyard. Scientists called it unprecedented. News anchors called it fascinating. Some people called it terrifying. But here's what nobody told you. 3I Atlas is nothing. It's a pebble, a snowflake, a cosmic footnote in a story that's about to get much, much bigger. Because while everyone was watching that interstellar scout zip past us, something else has been moving. Something that makes 3I Atlas look like a grain of sand next to a mountain. We're talking about Bernardinelli Bernstein, and if you haven't heard that name yet, you're about to hear it a lot. This isn't just another comet. This is what astronomers are calling a megacomet. Some are even calling it a minor planet. The nucleus alone measures 137 kilometers across. To put that in perspective, that's roughly the distance from Washington, D.C. to Philadelphia. Imagine an ice mountain that size, and then imagine it hurtling through space toward the inner solar system. That's what we're dealing with. This thing came from the Oort Cloud, that distant, frozen shell at the edge of our solar system, where comets go to sleep for millions of years. The Oort Cloud is the solar system's deep freeze, a vast spherical cloud of icy bodies orbiting somewhere between 2,000 and 100,000 astronomical units from the Sun. 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. So we're talking about objects so far away that sunlight takes months to reach them. These are the leftovers from the solar system's formation, the building blocks that never quite made it into planets, just frozen out there in the dark, waiting. Bernardinelli Bernstein is the largest comet nucleus ever measured. Not just large, the largest. By a significant margin. And it didn't just appear yesterday. The discovery story itself is fascinating. Astronomers Pedro Bernardinelli and Gary Bernstein found it by mining archival data from the Dark Energy Survey, images taken between 2014 and 2018. When they first spotted it, the comet was already inside our solar system, cruising at about 29 astronomical units from the Sun, roughly near Neptune's orbit. But here's where it gets interesting. When they went back through even older images, they found it in pre-covery observations going back further, out to about 34 astronomical units. This thing has been approaching for years, and we're only just now noticing it. Why didn't we see it before? Because nothing like this has ever been found so far out, while still being detectable. Oort Cloud comets are supposed to be small, dormant, invisible, until they get close enough to the Sun to wake up. Bernardinelli Bernstein breaks that rule. It challenges everything we thought we knew about distant comets. The old model said objects this far out should be inactive, frozen solid, essentially invisible rocks of ice drifting in the darkness. But this one is different. This one is massive enough and active enough that we can see it from billions of miles away. And then came 2025. This year brought the breakthrough that changed everything. Using the Atacama Large Millimeter Array, that collection of 66 radio telescopes in the Chilean desert that can peer into the coldest, darkest corners of space, astronomers detected molecular activity from Bernardinelli Bernstein at 16.6 astronomical units from the Sun. They found carbon monoxide gas jets erupting from the nucleus. Clear, unmistakable signs of outgassing. This is the first time anyone has securely detected this kind of activity from this megacomet, and the implications are staggering. Carbon monoxide jets at 16.6 astronomical units. Let that sink in. That's more than halfway out to Neptune. Out there, sunlight is weak, barely a trickle of energy compared to what Earth receives. Water ice doesn't sublimate at those distances. The frost line, where normal comets typically wake up and start outgassing, is much closer to the Sun. But Bernardinelli Bernstein isn't waiting. It's already active, already releasing gas, already showing signs of life, far beyond where it should. That means something unusual is happening. Either this comet is packed with super-volatile ices, compounds like carbon monoxide, carbon dioxide, nitrogen, or methane that can sublimate at incredibly low temperatures, or there's some other mechanism at work that we don't fully understand yet. This transforms our entire understanding of how Oort Cloud giants behave. These aren't supposed to be dynamic objects. They're supposed to be sleeping relics, frozen fossils from the solar system's birth, inert until they get close to the warmth of the Sun. But here's Bernardinelli Bernstein, a sleeping colossus stirring to life billions of miles out, cracking open like an ancient time capsule that's been sealed for 4.5 billion years. The comet is essentially sneezing carbon monoxide into space while still in the outer reaches of the solar system, and nobody quite knows why. For scientists, this is the opportunity of multiple lifetimes. Objects like this don't come around often. In fact, they might not come around at all in human history. This could be the first and only time a comet of this size, from this origin, passes through the inner solar system during an era when humans have telescopes powerful enough to study it. We're talking about a pristine sample of the early solar system, a frozen archive of the conditions and materials that existed when the planets were forming, now making its way inward, where we can actually observe it, measure it, analyze it. But here's what makes this story more than just a scientific curiosity. This isn't about watching a pretty tail streak across the sky. This is about a massive, ancient, volatile object entering the inner solar system over the next few years, behaving in ways that don't match our models, waking up earlier than it should, releasing gases that suggest an interior composition we can barely guess at. And if Bernardinelli Bernstein is doing this, if it's showing us that megacomets from the Oort Cloud can be active and dangerous and unpredictable, what does that say about all the others we haven't seen yet? What does that say about the population of hidden giants lurking in the dark edges of our cosmic neighborhood? Because here's the question nobody's asking publicly, but everyone's thinking privately. Is Bernardinelli Bernstein a freak? A one-time cosmic accident? Or is it the first of many? Could there be dozens, hundreds, thousands of these ice mountains sleeping in the Oort Cloud, and we're only now developing the tools to detect them? And if something disturbed this one enough to send it our way, what else might be following? Now that you know what Bernardinelli Bernstein is, you probably want to know where it's going. And more importantly, when it's getting there. The orbit of this megacomet is something straight out of a cosmic thriller. It comes from the Oort Cloud with a semi-major axis of roughly 20,000 astronomical units on the inbound leg, with an aphelion, that's its farthest point from the Sun, somewhere around 42,000 astronomical units. To give you context, that's about 700 times farther from the Sun than Earth is. Out there, The sun is just another star in the sky, barely brighter than others. Out there, temperatures hover just above absolute zero, and nothing moves quickly. But Bernardinelli Bernstein is moving now. It's on a long period orbit, meaning it takes millions of years to complete one full trip around the sun. The comet is plunging inward on a trajectory that will bring it to perihelion, its closest approach to the sun, around January 2031. And that perihelion distance is about 10.95 astronomical units, just beyond Saturn's orbit. Think about that for a moment. In 6 years, this mountain of ice will be closer to us than it's been in millions of years, possibly closer than it's ever been. Before you panic, let's be clear. Bernardinelli Bernstein is not going to hit Earth. Perihelion at roughly 11 astronomical units means it stays far outside Earth's orbit. There's no collision scenario here, no Hollywood ending where Bruce Willis has to fly up and plant bombs on an ice comet. This is not an extinction-level threat in the traditional sense. But just because it won't hit us doesn't mean it's not important. From a scientific and observational standpoint, this is massive. We're going to have a front row seat to watch a pristine Oort Cloud giant activate, evolve, and potentially do things we've never seen before. As of late 2025, the comet is currently about 14.5 astronomical units from the sun, moving gradually inward. That's roughly the distance to Uranus. Every day, every week, every month, it gets closer. And as it gets closer, things are going to change. More sunlight means more energy. More energy means more sublimation of volatile ices. More sublimation means more outgassing. We've already seen carbon monoxide jets at 16.6 astronomical units. As Bernardinelli Bernstein continues inward, those jets will intensify. We might see carbon dioxide outgassing start up. We might see water ice begin to sublimate once it crosses inside about 5 astronomical units, though that's still years away. The coma, that cloud of gas and dust surrounding the nucleus, will grow. If conditions are right, we might even see a dust tail develop, though given the comet's size and distance, it probably won't be the spectacular naked eye comet that casual stargazers dream about. This is going to be a slow motion spectacle. Between now and 2031, astronomers will have an unprecedented opportunity to monitor the evolution of a megacomet in real time. Ground-based telescopes will track changes in brightness, activity rates, and jet structures. Space telescopes might catch glimpses of it in infrared or other wavelengths. ALMA and other radio arrays will continue to study the molecular emissions, watching how the chemistry changes as solar heating increases. Every observation will add another piece to the puzzle of what this thing is made of, how it's structured, and how it behaves. Why does this matter so much? Because this is genuinely a once-in-a-lifetime window. Maybe once in many lifetimes. Bernardinelli Bernstein is possibly making its first passage through the inner solar system in millions of years. Some models suggest its previous perihelion was about 3.5 million years ago, and even then it only made it to about 18 astronomical units, never getting anywhere near as close as it will in 2031. This could be the comet's closest approach to the sun in its entire history, or at least in the last several million years. When it swings back out after perihelion, it'll retreat into the outer darkness, and we might never see it again in human civilization's time frame. If we don't study it now, the opportunity is gone forever. But there are challenges. Despite its enormous size, Bernardinelli Bernstein will remain relatively faint. The sheer distance means even at perihelion, it won't be bright enough for backyard telescopes to see clearly. This is a job for the big observatories, the professional-grade instruments. And comet behavior is notoriously unpredictable. Comets can have outbursts, sudden increases in activity. They can fragment, break apart under thermal stress or rotational forces. They can develop unexpected jets or lose activity entirely. With an object this large and this unusual, nobody knows exactly what to expect. The models give us a baseline, but models are only as good as the data they're built on, and we've never had data on anything quite like this. What we hope to learn is extraordinary. The composition of primordial ices locked away since the solar system's formation. The thermal properties of a massive comet nucleus. How heat penetrates and affects layers below the surface. How objects this large survive storage in the Oort Cloud for billions of years without disintegrating or losing their volatiles entirely. How they wake up. How the transition from dormant ice ball to active comet happens at a molecular level. And perhaps most intriguingly, how common these giants might be. If Bernardinelli Bernstein is out there, detectable, active, how many more are hiding in the dark that we simply haven't found yet? Because here's where the story takes a turn. If this comet behaves in unexpected ways over the next 6 years, if it shows odd activity patterns, if its orbit reveals anomalies, if the outgassing is stronger or weirder than models predict, that raises deeper questions. Questions about what's really happening in the Oort Cloud. Questions about whether this object's journey inward was a random nudge from galactic gravity, or whether something more specific, more directional, more unusual sent it our way. And if that's the case, if Bernardinelli Bernstein isn't alone, if this is just the first of a wave, then we need to talk about what that means for the hidden population of ice giants at the edge of our solar system. Let's go back to that ALMA discovery in 2025, because this is where the story gets scientifically weird and deeply fascinating. Astronomers pointed ALMA, the most powerful millimeter and submillimeter telescope array on Earth, at Bernardinelli Bernstein when it was 16.6 astronomical units from the Sun. They were looking for signs of activity, hoping to catch some kind of emission that would tell them the comet was waking up. What they found exceeded expectations. They detected the carbon monoxide spectral line at 230 gigahertz, a clear molecular signature of gas escaping from the nucleus. Along with that, they saw continuum thermal emission from the nucleus itself, confirming its large size and detecting possibly a faint dust coma surrounding it. But the carbon monoxide wasn't just leaking out evenly. The observations showed multiple jets, localized streams of gas erupting from specific regions of the nucleus. And here's the kicker. Those jets changed between observations. They evolved. That tells us the nucleus isn't a uniform block of ice. It has structure. There are hotspots, areas where volatile ices are concentrated, or where the surface has fractured enough to let gas escape more easily. This is a dynamic, active object, not a passive chunk of frozen material slowly warming up. The presence of dust is also significant. ALMA detected a compact continuum emission, consistent with not just the massive nucleus, but also a surrounding cloud of dust particles. So this isn't just a gas emission event. Dust is being lifted off the surface, or entrained in the gas flow, creating a rudimentary coma even at this enormous distance. That's unusual. Dust production typically requires significant gas flow to drag particles off the surface, and we're seeing that happen at a distance where solar radiation is incredibly weak. Why is this surprising? Because traditional comet models rely on the concept of a frost line or snow line. Inside a certain distance from the sun, different ices sublimate at different rates. Water ice, the most common comet component, sublimates efficiently inside about 5 astronomical units. Beyond that, water stays frozen. Carbon dioxide can sublimate farther out, maybe to 10 or 12 astronomical units. But carbon monoxide and other super-volatiles like nitrogen or methane can remain active much, much farther, out to 20 or even 30 astronomical units under the right conditions. The fact that Bernardinelli Bernstein is outgassing carbon monoxide at 16 to 17 astronomical units suggests its nucleus is rich in these super-volatile ices, compounds that formed in the coldest regions of the early solar nebula or were somehow preserved in unusually pristine condition. This challenges classical comet nucleus theory. Most comets we observe are relatively small, maybe a few kilometers across, and they become active when they cross inside the water frost line. Their activity is driven primarily by water ice sublimation, which produces the dramatic tails and comas we associate with comets. But Bernardinelli Bernstein is behaving differently. Its early activity, driven by super-volatiles, suggests a different composition or structure. Maybe its size means it retained more of the original volatile inventory from the solar system's formation. Maybe its storage in the Oort Cloud was cold and stable enough that even the most fragile ices didn't escape over billions of years. Or maybe there's something about its internal structure, layering of different ice types, trapped gases, pockets of volatile rich material, that makes it more prone to outgassing at large distances. If super-volatile-driven activity at large distances is common for big comets, that has huge implications for how we detect and understand Oort Cloud objects. Many distant bodies might stay completely undetected because they're dormant or only weakly active, but under the right circumstances, a nudge toward the sun, a bit more solar heating, they could turn on and become visible. We might be missing an entire population of massive comets simply because they haven't reached the threshold distance to start outgassing yet. Bernardinelli Bernstein could be the tip of a very large, very cold iceberg. And then there's the question of what this means for solar system history. Because the nucleus of this comet is so large and apparently so pristine, its volatile content could reflect the primordial composition of the early solar nebula. When the solar system was forming 4.5 billion years ago, a disk of gas and dust surrounded the young sun. Different regions of that disk had different temperatures and compositions. The inner regions were hot, rocky, depleted in volatiles. The outer regions, beyond the frost line, were cold enough for ices to condense. Water ice, carbon dioxide ice, carbon monoxide ice, ammonia, methane, all these compounds could freeze out and get incorporated into planetesimals, the building blocks of planets and comets. Bernardinelli Bernstein likely formed in one of the coldest regions, possibly beyond where Neptune is now, or even farther out. Its ices might preserve a record of what the outer solar nebula was like, what volatiles were available, and how those volatiles contributed to building the outer planets and eventually delivering water and organic molecules to the inner solar system, possibly to Earth. Studying the gases that Bernardinelli Bernstein releases as it approaches the sun could give us insight into the volatile distribution in the early solar system. What was the carbon monoxide to carbon dioxide ratio? How much nitrogen was there? What about methane, ammonia, or more complex organics? These ratios matter because they constrain models of planetary formation and migration. They tell us about the temperature and pressure conditions in different regions of the solar nebula. And they might even tell us something about the sources of Earth's water and organic molecules, the ingredients for life. But there's also the unknown factor. What we don't yet know about Bernardinelli Bernstein is as interesting as what we do know. Maybe the nucleus has internal inhomogeneities, layers of different ice types or rocky material that will affect how it heats and outgasses. Maybe there are old trapped gases, volatile bubbles sealed inside the ice for billions of years, waiting to burst out when the right layer sublimates. Maybe structural stress fractures will open up, causing sudden outbursts or even fragmentation events. Comets have been known to split apart, especially large ones under thermal or rotational stress. If Bernardinelli Bernstein starts breaking up as it approaches perihelion, that could create a dramatic increase in surface area and activity, or it could simply create a field of smaller fragments that behave differently. Think of this mega comet as a giant iceberg cracking open in deep space. It's a fossil from the solar system's dawn, suddenly sneezing carbon monoxide gas 500 million miles from the sun. It's a deep freeze vault beginning to leak its ancient secrets. And we're standing by with every instrument we have, trying to catch every molecule, every photon, every clue about what's inside. This isn't just astronomy. This is archaeology on a cosmic scale, excavating the history written in ice and gas. And that brings us to the bigger mystery. If Bernardinelli Bernstein is active this early, this far out, what does that say about how many other massive bodies might be lurking unseen in the Oort Cloud? If this comet is unusual, a statistical outlier, then we're incredibly lucky to see it. But if it's not unusual, if it's actually representative of a hidden population of ice giants waiting in the dark, then the Oort Cloud is far more dangerous and far more interesting than we ever imagined. Here's the uncomfortable question astronomers are starting to ask quietly in conference rooms and email threads and late-night conversations after symposiums. Is Bernardinelli Bernstein a freak, or is it normal? Because if it's a freak, a 1 in a billion cosmic accident, we can file it away as a fascinating anomaly and move on. But if it's normal, if objects like this are actually common in the Oort Cloud, and we've just been blind to them until now, then we need to fundamentally rethink what the outer solar system looks like and how dangerous it might be. Let's frame the puzzle. Historically, the comets we observe tend to be small, a few kilometers across, maybe 10 or 20 at most. They light up nicely when they get close to the sun, develop spectacular tails, become naked eye objects, make headlines, and then fade away. That's the pattern we know. Large comets are extremely rare in the observational record. Before Bernardinelli Bernstein, the largest well-measured comet nucleus was maybe 50 or 60 kilometers across, and even those were exceptional. So when something 137 kilometers wide shows up, active and detectable from billions of miles away, it raises an obvious question. Why haven't we seen more of these? One possibility is detection bias. Small comets are easier to spot than large ones in a counterintuitive way. Small comets have less mass, less gravitational binding, so when they start to outgas, the activity can be dramatic relative to their size. They flare up, become bright, get noticed. Large comets, on the other hand, have enormous mass. It takes a lot more energy to significantly heat a 137-kilometer ice ball than a 5-kilometer one. If most of the Oort Cloud's large objects stay cold and dormant, never receiving enough of a gravitational nudge to bring them close to the sun, they remain invisible. They're out there in the dark, massive and ancient and completely undetectable because they don't reflect much light and don't outgas. Bernardinelli Bernstein challenges that assumption. Here's a massive object that is active far from the sun, detectable, measurable, and apparently stable. That suggests maybe the population of large Oort Cloud bodies isn't as invisible as we thought. Maybe with better surveys, better instruments, better data analysis, we can find more of them. And if we can find more, that raises the next question. How many more are there? One scenario is that Bernardinelli Bernstein is genuinely an outlier. Maybe it formed in an unusual way, with an unusually high concentration of super-volatiles, and got nudged onto an unusually close orbit by a random gravitational interaction. A statistical fluke, a rare convergence of unlikely factors. If that's true, we might not see another one like it for centuries or millennia. We got lucky. We happened to develop telescopes powerful enough to detect it during the brief window when it's passing through the inner solar system. Enjoy the show, study it intensely, and don't expect a repeat performance. But the alternative scenario is more unsettling. What if Bernardinelli Bernstein is actually representative of a hidden population of Oort Cloud giants? What if there are dozens, hundreds, maybe thousands of objects this size or larger sitting out there in the dark, too cold to outgas, too far to reflect enough sunlight for detection, just waiting for a gravitational nudge? If that's the case, our census of outer solar system bodies is vastly incomplete. We've been counting the small active comets because those are the ones we can see. But the real mass, the real danger, might be locked up in these invisible giants. This has implications for the solar system mass budget. Current estimates of the Oort Cloud's total mass are based on the comets we observe and models that extrapolate from those observations. But if we're systematically missing the largest objects, those estimates could be wrong by a significant factor. Maybe the Oort Cloud contains 10 times more mass than we think. Maybe 100 times. That extra mass doesn't just sit there passively. It affects gravitational dynamics, long-term orbital evolution, the stability of the outer planets, and the frequency with which these objects get perturbed and sent inward. It also affects planetary formation models. If large bodies were common in the early solar system's outer regions, they would have played a role in scattering smaller planetesimals, in feeding material to the growing outer planets, in shaping the architecture of the Kuiper Belt and scattered disk. Understanding how many large comets exist and where they formed constrains theories of how Jupiter, Saturn, Uranus, and Neptune reached their current positions and masses. And then there's the practical question: what are the odds of future discoveries? With improved surveys, next-generation telescopes, more sensitive infrared, and sub-millimeter instruments, we're going to find more distant objects. The Vera Rubin Observatory, for example, once it's fully operational, will survey the entire visible sky every few nights, generating enormous datasets that can be mined for slow-moving, faint objects. AI and machine learning algorithms are getting better at spotting anomalies in massive datasets, at connecting dots between observations years apart, at identifying objects that human astronomers would miss. If Bernardinelli Bernstein is the first of many, we'll start seeing them pop up regularly. Maybe every few years, a new Bernardinelli-type object will be announced, each one adding to the picture of what the Oort Cloud really contains. But there's a risk in underestimating the unknown. If the population of large comets is bigger than we thought, even objects that only come into 10 or 20 or 30 astronomical units could have unexpected effects. They could gravitationally perturb smaller bodies in the Kuiper Belt or scattered disk, sending those on chaotic orbits that might eventually cross Earth's path. They could collide with each other out in the Oort Cloud, creating debris clouds or altering orbits in unpredictable ways. Over millions of years, cumulative effects from a large hidden population could reshape the outer solar system in ways we haven't accounted for in our models. There are also significant challenges and biases in detection. Many Oort Cloud objects never outgas, or outgas so weakly that we can't detect the emissions. Many are dark, with low albedos, reflecting very little sunlight. Survey coverage is limited. We can only watch certain parts of the sky at certain times, and objects on long-period orbits move slowly, making them hard to distinguish from background stars or galaxies without years of observations. Activity onset is unpredictable. A comet might be dormant for decades and suddenly turn on, or it might be active, but pointing its jets away from Earth so we don't see the emissions. All of these factors mean we could be blind to a substantial fraction, maybe most, of the massive comets in the Oort Cloud. Historically, we didn't notice this gap because we lacked the tools. Before digital sky surveys, before sensitive submillimeter arrays like ALMA, before automated data mining, algorithms finding distant, faint, slow-moving objects was incredibly difficult. Bernardinelli Bernstein was hiding in plain sight in archival data for years before anyone spotted it. How many others are still hiding in datasets we haven't fully analyzed? How many are in regions of the sky we haven't surveyed deeply enough? The fact that we found this one, this mega comet, using old data and new techniques suggests that the Oort Cloud is about to reveal a lot more secrets as our methods improve. Some researchers are starting to propose what could be called a comet iceberg hypothesis. Maybe 1 to 5% of the Oort Cloud's total mass is locked up in large dormant giants, objects bigger than 100 kilometers, and every few million years, one of these gets nudged inward by galactic tides or a passing star. Most of the time, they stay dormant, never getting close enough to the sun to activate and become visible. but occasionally, one takes a trajectory that brings it into the observable range, and we get a Bernardinelli Bernstein event. If that's true, the cosmic narrative changes. Comets aren't just small snowballs. They're occasionally mini-worlds, ancient ice mountains that have been sleeping since the solar system was young, waiting for the right disturbance to wake them up. And that leads directly to the next question, the one that keeps astronomers up at night. What caused Bernardinelli Bernstein to wake up now? What disturbed it? Was it a slow, random nudge from the galactic tide, the gentle gravitational tug of the Milky Way's mass pulling on the outer edges of the Oort Cloud over millions of years? Was it a passing star, a rogue brown dwarf, some dark object that flew through the Oort Cloud and kicked this comet onto its current path? Or is there something more exotic, more unsettling? Something we haven't considered yet? Now we wade into the speculative zone, the territory where hard science meets informed guesswork, and, occasionally, the kind of ideas that sound like science fiction, but aren't entirely impossible. Because the question of how Bernardinelli Bernstein ended up on its current trajectory is genuinely mysterious, and the answers we have are incomplete. Let's start with the scientific baseline. The standard model for Oort cloud dynamics says that objects in the cloud are occasionally perturbed by external gravitational influences. The primary culprit is the galactic tide, the differential gravitational pull exerted by the mass of the Milky Way galaxy itself. The Sun orbits the galactic center, and as it does, it moves through regions with slightly different gravitational fields. Over millions of years, these subtle differences tug on the distant Oort cloud objects, gradually changing their orbits. Some get nudged outward, escaping the solar system entirely. Others get nudged inward, toward the Sun, and eventually become observable comets. This is a slow process, statistical, affecting countless objects over vast timescales. Another mechanism is stellar encounters. The Sun isn't alone in space. Other stars pass relatively close, in galactic terms, every few million years. A star passing within a few light years of the Sun can gravitationally disturb the Oort cloud, sending a shower of comets inward. Some models suggest these encounters are responsible for periodic increases in comet activity, possibly even linked to mass extinction events on Earth when comet impacts increase. For Bernardinelli Bernstein, that's the accepted explanation. Some combination of galactic tide and maybe a distant stellar flyby over the last few million years nudged it onto its current path. But here's what we don't know. Orbital backward integrations, trying to calculate where the comet was in the past, suggest its previous perihelion was about 3.5 million years ago at roughly 18 astronomical units. So it's been on a long elliptical orbit, swinging out into the Oort cloud, coming back in, following the same path for millions of years. But those calculations have assumptions. They assume we know all the relevant gravitational influences: the Sun, the planets, the galactic tide, any known stellar encounters. If there was an unknown influence, an uncharted stellar flyby, a rogue object passing through, the calculations could be off. We don't have perfect knowledge of every star that's passed near the solar system over the past few million years, especially faint ones, brown dwarfs, or any hypothetical dark objects. Hypothesis 1. Rogue star or close stellar flyby. Imagine a star, or a brown dwarf, or even a large planet-sized object ejected from another stellar system, passing through or near the Oort cloud a few million years ago. The gravitational interaction could have kicked Bernardinelli Bernstein, altering its orbit enough to send it on its current trajectory. Stellar flybys happen. They're rare on human timescales, but common over millions of years. The challenge is that if the object was faint or dark, we might not have any record of it. Brown dwarfs are hard to detect, especially if they're not actively emitting much infrared radiation. A rogue planet would be nearly impossible to spot unless it happened to pass very close to something bright. So we could be dealing with an invisible interloper, something that disturbed the comet and then moved on, leaving no trace except the altered orbit. Hypothesis 2. Hidden massive companion. This is where we enter speculative territory. Some theories propose the existence of a distant, massive object orbiting the Sun far beyond the known planets. Various names have been floated: Planet 9, Planet X, a dark companion. The idea is that this object, perhaps a super-Earth or sub-Neptune-sized planet, orbits at several hundred astronomical units or more, and its gravity occasionally disturbs Oort Cloud objects. Bernardinelli Bernstein's orbit has a steep inclination of about 95 degrees, meaning it plunges almost perpendicular to the plane of the solar system. That orientation is unusual. Most planets and most Kuiper Belt objects orbit roughly in the same plane. An orbit tilted 95 degrees suggests the object was either formed in an unusual way or had its orbit significantly altered by something. Could a distant massive planet have done that? It's possible, but there's currently no evidence for such a planet. Searches have turned up nothing definitive. If it exists, it's either very far away, very faint, or we've been looking in the wrong places. Hypothesis 3. Internal or non-standard activation mechanisms. Maybe Bernardinelli Bernstein's awakening isn't just about solar heating. Maybe there's internal heat generation happening. Radiogenic heating from the decay of radioactive isotopes inside the nucleus could provide a baseline warmth that helps volatiles sublimate even at large distances. Or maybe the comet's structure is such that mechanical stress from rotation or internal pressure causes cracks to open up, exposing volatile-rich layers to space where they can outgas. This wouldn't explain the orbit, but it would explain the early activity, the carbon monoxide jets at 16.6 astronomical units. It's a possibility, though it requires some unusual internal conditions. The steep inclination is worth emphasizing. Orbits inclined close to 90 degrees or more are called polar or retrograde orbits. They're rare in the solar system. The planets orbit in roughly the same plane because they all formed from the same protoplanetary disk. Most Kuiper Belt objects and scattered disk objects also have relatively low inclinations. When you find something with a 95-degree inclination, it suggests that object either formed in a very different environment, or its orbit was dramatically altered after formation. For Bernardinelli Bernstein, coming from the Oort Cloud, the inclination could just be random, the result of countless small perturbations over billions of years. But it could also be the result of a single, large perturbation, a directional disturbance that kicked the comet onto a near-perpendicular path. If the latter, what was the source? Now, let's be clear about the balance between evidence and speculation. The mainstream explanations, galactic tide, and stellar perturbations are well supported by models and observations. There's no credible evidence for a rogue star, a hidden massive companion, or internal heat sources driving Bernardinelli Bernstein's orbit or activity. These ideas are speculative, interesting to think about, useful for exploring possibilities, but not scientifically established. No peer-reviewed paper currently claims that this comet's motion is anything other than natural. There's no sign of engineered motion, no evidence of alien intervention, no indication that anything non-natural is happening here. But speculation matters for the narrative. Even if these ideas are unproven, they fire up the imagination. They force us to ask questions about what we don't know. What if the Oort Cloud isn't just a passive storage zone, but a volatile, active frontier occasionally stirred by dramatic events? What if there are objects out there, dark and massive and invisible, that we simply haven't detected yet? What if Bernardinelli Bernstein is the first of a wave of comets, triggered by something we don't understand, and more are coming? Consider some potential what-if scenarios. What if this is the first of several mega-comets triggered by the same event, a stellar flyby or gravitational disturbance that sent multiple objects inward on different timescales? What if a hidden astrophysical companion exists, and it's slowly clearing out the Oort Cloud, sending a steady stream of comets our way over the next million years. What if the Oort Cloud is far more dynamic than we thought, with internal collisions, tidal forces, and structural evolution happening constantly? And Bernardinelli Bernstein is just the most visible symptom of an ongoing process. These ideas are like cosmic dominoes. One event triggers another, which triggers another, in a cascade we can't yet predict. Or think of it as sleeping giants scattered across the outer edges of the solar system, and something just walked through and started waking them up one by one. Or a hidden deep freeze vault slowly unlocking, its contents spilling out into the light. The metaphors matter because they help us grasp the scale and the stakes. And here's the thing, we're about to have better tools to find out. Over the next decade, improved telescopes, wider surveys, more sensitive instruments, and more powerful data analysis using artificial intelligence and machine learning will reveal far more about the outer solar system. If there are more megacomets out there, if there's a hidden population waiting to be discovered, we're going to find them. And when we do, we'll start to see patterns. We'll see whether Bernardinelli Bernstein is unique or common, whether its orbit is random or part of a larger structure. We'll get answers. But the questions we're asking now, the speculations we're entertaining, they set the stage for what's coming next. Bernardinelli Bernstein isn't happening in a vacuum. While everyone's attention is focused on this one megacomet, other things are happening in the solar system that frame the story in important ways. We're in the middle of a renaissance in outer solar system astronomy, a period where new discoveries are coming faster than ever, and the picture we're building of the distant reaches of our cosmic neighborhood is getting stranger and more complicated. Start with this context. Astronomers are increasingly detecting distant, long-period comets and unusual objects from the outer solar system. The number of known comets with unusual orbits or distant perihelia has been growing steadily over the past decade. Some of these are being found through active surveys, telescopes, systematically scanning the sky night after night. Others are being discovered by mining archival data, going back through old images with new algorithms that can spot faint, slow-moving objects that were missed the first time around. The trend is clear. The Oort Cloud is slowly revealing its secrets, and those secrets suggest a more active, more populated region than we previously thought. There have been several notable detections in recent years of comets behaving in unexpected ways. Long-period comets that activate far from the sun, similar to Bernardinelli Bernstein. Objects with extremely high inclinations or retrograde orbits, suggesting they come from distant, randomly oriented regions of the Oort Cloud. Some comets have shown unusual outgassing patterns, jets that don't align with solar heating models, or chemical compositions that challenge expectations. Each discovery adds to a growing realization. The comets we've been studying for centuries, the classical short-period and moderately long-period comets, might not be representative of the full diversity of objects in the outer solar system. Why are we seeing this wave of discoveries now? It comes down to the power of modern astronomical tools. ALMA, the Atacama Large Millimeter Array, can detect molecular emissions from incredibly faint, distant sources, giving us a way to spot comets through their gas output even when they're too far or too faint for optical telescopes. Powerful ground-based telescopes with adaptive optics and sensitive detectors can pick up faint reflected light from distant objects. Space-based infrared telescopes can detect the thermal emission from cold bodies that would be invisible in visible light. Wide-field survey telescopes can image huge sections of the sky repeatedly, building up datasets that allow for the detection of slow-moving objects by comparing images over time. All of these technologies have matured in the past decade or two, and the result is a flood of new data. Then there's the role of data mining and archival searches. Surveys like the Dark Energy Survey weren't designed to find comets. They were looking for galaxies, supernovae, other cosmological phenomena. But the images they took happened to capture everything in the field of view, including faint solar system objects. By going back through those archives with modern detection algorithms, researchers like Bernardinelli and Bernstein can find things that nobody was specifically looking for at the time. And with machine learning techniques getting better, with AI systems that can recognize the subtle patterns of a slowly moving object against a background of stars, this kind of archival discovery is going to become more common. There could be dozens more Bernardinelli Bernstein scale objects hiding in data that's already been collected, just waiting for someone to run the right analysis. The growing realization is that the outer solar system is a dynamic frontier. It's not a quiet, distant reservoir of frozen leftovers. It's an active environment where objects are being perturbed, where orbits are evolving, where new visitors are arriving all the time. Some come from the Oort Cloud, nudged inward by galactic tides or stellar encounters. Some come from the scattered disk, objects with chaotic orbits that occasionally swing close to the sun. Some might even be interstellar interlopers, like Oumuamua or 2I Borisov, passing through from other star systems. The edges of the solar system are becoming more interesting, more crowded, more unpredictable than we thought. If this trend continues, and there's every reason to think it will, we're going to see dozens more Oort Cloud comets over the next few decades. Maybe not all of them will be as large as Bernardinelli Bernstein, but many will be unusual in some way. Unusual compositions, unusual orbits, unusual activity. Each one will teach us something new about the outer solar system's structure, its history, its current dynamics. We'll start to build a statistical picture of what the Oort Cloud really looks like, how many objects it contains, what sizes and compositions are common, how often they get perturbed inward. And that has implications. If large comets are more common than we thought, their cumulative effects over millions of years could be significant. Gravitational interactions between comets and the outer planets could affect planetary orbits over long timescales. Collisions or near misses between large comets and moons or minor planets could create debris clouds or alter surface features. The influx of cometary material into the inner solar system could have effects on planetary atmospheres, on the delivery of water and organics to terrestrial planets, on the overall architecture of the solar system. There's also a potential risk factor. Most long-period comets pass harmlessly through the inner solar system without coming close to Earth. But with more comets being discovered, with a better understanding of their population and orbits, we might eventually find one that has an Earth-crossing trajectory. The odds of a direct impact are incredibly small, but the consequences would be catastrophic. Even a near miss by a large comet could have effects. Gravitational perturbations on near-Earth asteroids, or cometary debris entering Earth's atmosphere. Planetary defense, the field of detecting and mitigating asteroid and comet threats, is going to have to account for these long-period visitors that appear with little warning. Now, here's a provocative question, a speculative angle that's worth considering, even if it's not scientifically established. Are we waking up the Oort Cloud? Is something happening right now in our current era that's increasing the rate at which Oort Cloud objects are being sent inward? Some researchers have speculated about galactic tide cycles, periods when the sun's position in the galaxy makes Oort Cloud perturbations more likely, or shifts in the local stellar neighborhood, clusters of stars moving through the region, increasing the frequency of close encounters. There's no strong evidence for this, no clear signal that we're in a special period. But the increase in discoveries could be partly observational bias. We're just getting better at finding them, and partly real, more objects are coming in because of some long-term galactic process. If we are entering a phase of increased Oort Cloud discharge, that's significant. It means the next century or millennium could see more large comets, more unusual visitors, more opportunities to study pristine material from the solar system's formation. For science, that's fantastic. For humanity's long-term safety, it's something to keep an eye on. Either way, The narrative is shifting from the Oort Cloud is a distant, quiet region we barely understand to the Oort Cloud is an active, dynamic reservoir that occasionally sends us reminders of what's out there. For humanity, this matters in multiple ways. More opportunities to study comets means more data about the early solar system, better understanding of how planets formed, how water and organics were delivered to Earth, what the building blocks of life looked like. For astronomy, these comets are test beds, natural laboratories where we can study processes that we can't replicate in labs on Earth. For planetary defense, understanding the population and dynamics of long-period comets helps us assess risks and prepare for potential threats. And on a philosophical level, these discoveries remind us that we live in a vast, complex, evolving cosmic environment, and we're only just starting to map it. The story of Bernardinelli Bernstein isn't just about one comet. It's about an awakening outer solar system, a frontier that's revealing itself slowly, one discovery at a time. And as our tools improve, as our surveys get deeper, as our algorithms get smarter, we're going to see more, much more. This is just the beginning. We're living through a transformation in astronomy that's happening so fast and so quietly that most people don't realize it's even happening. The tools, the data, the techniques we use to explore the cosmos have changed more in the past decade than they did in the previous century. And that transformation is what allowed us to discover Bernardinelli Bernstein in the first place, what's allowing us to study it now, and what's going to let us find many more objects like it in the years to come. Start with the telescopes. Modern astronomy relies on instruments that would have seemed like science fiction a generation ago. ALMA, the Atacama Large Millimeter Array, is an array of 66 radio dishes working together as a single instrument, capable of detecting molecular emissions from objects billions of miles away with exquisite sensitivity. Ground-based optical telescopes with mirrors 10 meters across or larger, equipped with adaptive optics that correct for atmospheric turbulence in real time, can image faint objects with resolution that rivals or exceeds space telescopes. Space-based infrared telescopes can detect the faint heat signatures of cold objects in the outer solar system. And wide-field survey telescopes, like the upcoming Vera Rubin Observatory, can image the entire visible sky every few nights, generating petabytes of data that capture everything from distant galaxies to nearby asteroids to slow-moving comets at the edge of the solar system. But the telescopes are only half the story. The real revolution is in data analysis. Bernardinelli Bernstein was discovered not by someone sitting at a telescope eyeballing images, but by mining archival data from the Dark Energy Survey using sophisticated algorithms designed to detect slow-moving objects. That's the new paradigm. Surveys generate enormous datasets, far more than any human could examine manually. Those datasets sit in archives, and researchers develop algorithms, often using machine learning and artificial intelligence techniques, to search for specific signals. Moving objects, transient events, spectral signatures, anything that doesn't fit the expected pattern. Artificial intelligence and machine learning are changing the game for comet discovery. Traditional methods relied on comparing images taken at different times and looking for objects that moved. That works, but it's labor-intensive and prone to missing faint objects or objects that move slowly. Modern algorithms can process thousands of images simultaneously, identifying candidate objects, tracking their motion, filtering out false positives, and flagging the most interesting targets for follow-up observations. They can even predict where an object might be in future observations, allowing for targeted searches. This means we can find objects that would have been impossible to detect with older methods, especially long-period comets from the Oort Cloud that move slowly and might take years to cross from one image to the next. And this is just the beginning. Future surveys will generate even more data. The Vera Rubin Observatory, once fully operational, will produce something like 15 terabytes of data per night. Over the course of a decade, it will map the entire sky visible from its location in Chile hundreds of times, creating a time-lapse movie of the universe. Every asteroid, every comet, every supernova, every variable star, captured and cataloged. AI systems will be essential for making sense of that data, for finding the signals hidden in the noise, for identifying the rare, unusual objects like Bernardinelli Bernstein that only appear once in a generation. The broader scientific significance of Oort Cloud giants like Bernardinelli Bernstein can't be overstated. These objects are time capsules. They formed 4.5 billion years ago in the outer regions of the solar nebula, when the sun was still surrounded by a disk of gas and dust that would eventually coalesce into planets. They contain ices and organic molecules that were present in that primordial disk, the raw materials that built the solar system. By studying their composition, the ratios of different isotopes, the types of molecules present, we can learn about the conditions in the early solar system. What was the temperature in different regions of the nebula? How were volatiles like water, carbon dioxide, carbon monoxide, methane, ammonia distributed? How did those volatiles end up on planets like Earth, contributing to our oceans and atmosphere, and maybe even the chemistry that led to life? There's also a potential long-term resource angle, though this is highly speculative and far in the future. If humanity ever expands into the outer solar system, icy bodies like comets and Kuiper belt objects could be valuable. They contain water ice, which can be split into hydrogen and oxygen for fuel and life support. They contain carbon and nitrogen compounds, useful for agriculture and manufacturing. They contain organics that could be feedstock for chemical synthesis. A single large comet, like Bernardinelli Bernstein, contains more water than all the lakes on Earth combined. Of course, accessing that material would require technology and infrastructure we don't currently have, and the comet is moving, so catching it and mining it would be an extraordinary challenge. But in the long-term economics or science of space, these icy giants might become important. On a philosophical level, the discovery and study of Bernardinelli Bernstein forces us to confront our place in the cosmos. We tend to think of the solar system as something familiar, mapped, understood. We know the planets. We've sent probes to most of them. We've landed on Mars and the Moon. But the solar system is vast. The distance from the Sun to Neptune, about 30 astronomical units, is just a tiny fraction of the solar system's true extent. The Oort Cloud reaches out to 100,000 astronomical units or more, a sphere of icy bodies orbiting in the frigid darkness at the very edge of the Sun's gravitational influence. That's the real edge of our solar system, and it's full of mysteries. Bernardinelli Bernstein comes from that frontier, a reminder that there are ancient, massive, dynamic things happening out there that we're only just beginning to understand. These distant bodies also remind us that the solar system isn't static, it's evolving. Orbits change, objects get perturbed. Occasionally, something gets nudged inward and passes through the inner system, briefly visible before retreating back into the dark. We're lucky to be here at a time when we have the tools to observe these events, to study them, to learn from them. A few centuries ago, a comet like Bernardinelli Bernstein would have been invisible, undetectable, maybe glimpsed as a faint, fuzzy patch in a telescope, but not understood. A few centuries from now, we'll probably have even better tools, maybe space-based telescopes in the outer solar system, maybe probes that can intercept and study comets up close. But right now, in this moment, we're at a unique point in history where we're just good enough to see what's out there, just smart enough to ask the right questions, but not yet good enough to answer all of them. There's also a cautionary note that needs to be stated clearly. Speculation is valuable. It drives curiosity. It generates hypotheses. It pushes us to think beyond the obvious. But speculation is not evidence. The ideas we've explored here, rogue stars, hidden companions, internal heat sources, waves of comets triggered by unknown events, these are possibilities, not established facts. The evidence we have points to natural, understood processes: galactic tides, stellar perturbations, super-volatile ices sublimating at large distances. That's the baseline. Anything beyond that requires extraordinary evidence before it can be accepted as real. Science depends on skepticism, on rigorous observation, on testing ideas against data. So, while it's fun and valuable to ask, what if, it's equally important to ask, what does the evidence actually show? And to be honest, when the answer is, we don't know yet. For anyone following this story, and you should be, there are concrete things to watch for. Upcoming observations of Bernardinelli Bernstein using ALMA, optical telescopes, infrared instruments, all of these will add to the picture. As the comet continues inward toward its 2031 perihelion, it will get brighter, more active, easier to study. New surveys like the Vera Rubin Observatory's Legacy Survey of Space and Time will discover more distant objects, potentially more megacomets, more unusual Oort Cloud visitors. Data from these surveys will be publicly available, and amateur astronomers, citizen scientists, and professional researchers alike will be able to contribute to the analysis. This is a communal effort, a collective attempt to understand the solar system's outer frontier. So where does that leave us? We're witnessing the awakening of a cosmic giant. Bernardinelli Bernstein, a 137-kilometer wide mountain of ice and rock and frozen gases, is plunging toward the inner solar system, outgassing carbon monoxide jets billions of miles from the sun, behaving in ways that challenge our models and force us to rethink what we know about the Oort Cloud. We don't know yet how many more objects like this are lurking in the dark. We don't know exactly what triggered its inward journey. We don't know what secrets its ices will reveal as it continues to warm. But we're watching, we're measuring, we're learning. And maybe that's the real point. Science is a process, not a destination. Every answer we find generates new questions. Every discovery opens new frontiers. Bernardinelli Bernstein isn't the end of the story. It's a chapter, an important one, but part of a much longer narrative about how the solar system formed, how it evolved, how it continues to change, and how we, as curious beings lucky enough to exist at this moment in cosmic history, are figuring it all out. The story of our solar system's distant frontier is only beginning to unfold. The Oort Cloud is waking up, and we're here to see it.